So we will now find out the energy carried by electromagnetic waves. So wherever there is an electric field E, we can assign an energy density for that electric field. And we know that the energy per unit volume due to that electric field, which we denote by mu E, can be written as half of epsilon naught times E squared. And there is an analogous equation for magnetic field B as well, where mu B is the energy per unit volume due to magnetic field. So in an electromagnetic wave where both the fields are present, the electromagnetic energy density can be written as the summation of the above two quantities. And we know the relation between E and B. So converting this B into E by this equation tells us that these two quantities are actually the same. So the electromagnetic energy density in terms of the electric field only can be written as epsilon naught times E squared, and in terms of magnetic field only it can be written as B squared divided by mu naught. And energy density can be written like this if we use both E and B. Now if we want to find the total energy, we have to multiply this energy density with a volume element. Now let us consider a volume element like this in the path of an electromagnetic wave. Let's say the electromagnetic wave is passing through this area A. Now the total energy in this small cubic volume will be equal to energy density times the volume of this cube. Now if we want to find out the energy per unit time crossing this area A, we have to divide this energy by the interval of time that is required to pass this distance delta x. Now as the wave passes at a constant velocity c, we can write down delta t to be equal to this distance divided by the speed of light c. So if we put this delta t in this equation, we get mu times AC. Remember that this mu is the energy density, not the permeability of magnetic field. Okay, so now if we want to know the energy per unit time per unit area, what should I do? Well, we have to divide this quantity by the area A. So we get energy density times the speed of light. And if you put the value of the energy density in this equation, you will get the energy per unit time per unit area to be equal to E times B divided by epsilon naught. Now this thing here can be considered as a vector quantity if we write E times V as a cross product. Then this becomes the S vector, which is commonly known as Poynting vector. So what does this S mean? Well, this S is the flow of electromagnetic energy traveling through the space per unit area and per unit time. And if we put different expression of the energy density in this equation, we get different expression for this S, which is just the magnitude of this Poynting vector. We can call this S to be simply power per unit area. Now we can also define a term which is known as the intensity of the electromagnetic wave to be equal to the average power per unit area. So let us find out the expression for this intensity. Now the magnitude of the Poynting vector takes this form when we write it in terms of the electric field only. Let's say at some point Q, the electric field takes this form, where EM is the amplitude of the electric field wave. And if we put this value in this equation, the magnitude of the Poynting vector then takes this form. And we defined intensity to be the time average of the magnitude of the Poynting vector. Now, in order to evaluate this average, we can take these constant terms outside and take the average of this cos squared. And we know that the average of a cosine square of an angle is equal to half. So intensity can be written as equal to half times this quantity. Now sometimes this result is written in terms of the RMS value of the amplitude of electric field, which is defined as EM divided by square root of 2. And using this definition of ERMS, we can write down intensity to be equal to epsilon naught times ERMS. Okay, so now let us prove an important fact that intensity decreases with distance from the source. So let's say we have a source which is constantly emitting energy all over the space. Let's say the power of the source is PS. Now if we imagine a sphere like this, then the average power per unit area should be equal to the power of this source divided by the area of this sphere. So that means that we can write that this power of the source is equal to the average power per unit area for this surface times the area of this surface. And if we consider this sphere now, well, then again we can write the power of the source to be equal to the average power per unit area for this surface times the area of this sphere, which is this quantity. Now you know that the average power per unit area can be written as the intensity, right? So then we'll have this equation which relates intensity at distance r1 and at distance r2. And as you can see from this relation that intensity is actually inversely proportional to the distance squared. Now here is a simple problem for you where you have to find out the amplitude of the electric wave EM and then ERMS. For this problem we have an isotropic point source with power of 250 watt. It's a very easy problem and you can try this on your own.